If log base 7 minus a of 2x squared plus 2x plus a plus 3 is defined for all real x, find the possible values of a, giving your answer in interval notation. So here we have a function, and we're told that it's defined for all real values of x, which means that no matter what value of x I plug in, this produces a sensible answer. It gives me something that makes sense. And we're trying to find the possible values of a, which would allow for that to happen. Now we know that for a log to be defined, the argument of the log, or the thing that we plug into the log, has to be strictly greater than 0. So that's going to constitute part of my solution. But then we also know that there are some restrictions on what the base can be. So that's also going to constitute part of my solution. So this is really going to be comprised of two parts. It's going to be the argument, the thing inside of the logarithm, and the base of the logarithm. Let's start with the argument. So we know that for a logarithm to be defined, we must only plug positive numbers into the logarithm. So we're going to want 2x squared plus 2x plus a plus 3 to be greater than 0. Now, if we graph this, it looks like a parabola. And of course, the parabola is going to change depending on the value of a. But all a is going to do is it's just going to shift my parabola up or down by a certain amount. It's going to stay on the same axis because the a is only influencing the constant, which is shifting the parabola up or down. Now, if we want this to always be positive, well, we want this parabola, which is concave up because the coefficient is positive, the leading coefficient, we want this to never touch or go below the x-axis. In other words, we want this parabola to never have any roots. And when I start talking about roots of a parabola, that suggests to me that I need to work with the discriminant. So here's how I would set out this part of the solution. I would say that we want 2x squared plus 2x plus a plus 3 to be greater than 0. Okay. Now, in order for this to happen, I know it's already concave up. And for it to always be greater than 0, I want it to never touch the x-axis. I want it to never cross the x-axis, which means I want my discriminant to be less than 0 in order for there to be no roots. So therefore, we want delta to be less than 0. Now, what's delta in this case? It's b squared minus 4ac. So it's 2 squared minus 4 times a times c, which is a plus 3. And I want that to be less than 0. So that's 4 minus 8 into a plus 3 is less than 0. And now it's just a matter of solving for a. So let's see, 4 is less than 8 into a plus 3. A half is less than a plus 3. And if I subtract 3 from both sides, I'll have that a must be greater than negative 5 on 2. So this is going to be one of the conditions that must be satisfied in order for this function here, in order for that function to be defined for all real values of x. But of course, that's not the only part that we need. We also have to take care of our base. Now, what do we know about the base of a logarithm? Well, we know that the base of a logarithm has to be greater than 0, but then there's also one other condition that we need. But let's first deal with the fact that it has to be greater than 0. So I'll say we also need 7 minus a to be greater than 0, which means we need a to be less than 7. But the other condition that we need is that the base of our logarithm cannot be equal to 1. So 7 minus a can't be equal to 1. So I'm going to say and 7 minus a cannot be equal to 1. In other words, a cannot be equal to 6. So I need to be greater than negative 5 on 2 and less than 7 while simultaneously not being equal to 6. Now, if you're unsure about why the base can never be equal to 1, I'll explain that at the end of the video. But let's just complete the question now, write it out in interval notation, and make sure that we've answered the question. So therefore, I need a to go from negative 5 on 2, not including negative 5 on 2, up to 6, I want to exclude 6, and then I want to continue from 6 up to 7, and I want to exclude 7. And so that there is the final solution for this question. Now, if you're wondering why 1 can't be the base of a logarithm, then let's consider the following. What does it mean when we take a logarithm? Well, let's consider a simple example. Log base 2 of 8. Now, when I look at something like this, what I understand of it, I know that the answer to this is 3, but I can rephrase this in a certain way. I can write this as 2 to the power 3 equals 8. And that's the understanding we have between logarithms and exponentials. But how am I actually understanding the logarithm? That's what's important here. Well, when I say log base 2 of 8 equals something, what I'm asking myself is, what is the number that I have to raise the base to? I have to raise the number 2 to in order to get 8. And of course, that number is 3. So we can do another example. Log base 5 of 125. Again, actually, this is going to be 3 as well. And the way I understand this is, what number do I have to raise the number 5 to in order to get 125? And of course, we know that this is equivalent to just saying 5 cubed equals 125. So now I can ask myself, what happens if I consider a base of 1? Log base 1 of, let's say, 10. What's that equal to? Well, let's rewrite it in this way. What number do I have to raise 1 to? Actually, let me write that 1 in green. 1 to the power of what? Let's call it x because we're not sure. 1 to what power gives me 10? Well, of course, this doesn't have any solution because 1 to any power is just 1. I can't get the number 10. So this is an undefined operation having log in base 1. And so that's why we had to exclude up here the case where the base was equal to 1.